All right, hello everybody. Welcome to 5.4 Part B. This is called Special Functions. Hopefully in 5.4 Part A, where we looked at function notation, right, we changed from saying y equals m, or y equals, we can put real numbers in, 3x plus 7. We said, this is correct, and we will call this standard notation. But instead of writing it like that, we are allowed to write things, I guess I have a blank page right here, write things like f of x equals 3x plus 7, and that's totally okay. And actually we should get used to seeing things in this function notation. Now we're going to kind of put this f of x form, this function notation, on hold for just a second, and we are going to look at what in this section that we just call special functions. And I'll give you a little preview of what that means. So far we have seen almost all, if not all, of our functions be in the form y equals mx plus b, this linear form, where remember m is our slope and b is our y-intercept. And all of these functions make some type of line on our graph, right? Just some type of straight line or consistent line on our graph. Now, today we're going to look at special functions. So that means that not all of them are going to be just a normal line like we're used to. And I guess I'll leave the preview at that. We're going to see some different types of functions. So our learning targets. Students will be able to evaluate, solve, and graph functions written in function written in function notation. That was more of what we looked at in Part A. We still are going to need to evaluate, solve, and graph functions, but they won't be in the form of f of x or in function notation. Students will be able to compare graphs of linear functions. So what we're going to look at is something that maybe we're familiar with, but it's called a parent function. And a parent function would be really one of these functions, one of these graphs at its very basic. So like I said, we've looked a lot at y equals mx plus b with a slope and a y-intercept. The parent function would be y equals x, where we have a consistent, perfectly straight line that goes right through 0, 0, and that has a slope of 1, 1. That would be the parent function right here with no numbers attached, the parent function for the slope-intercept form. So we're going to look at some other parent functions. The first type of special function that we are going to take a look at is called a piecewise function. And you can see, well, you will see very soon why it's called a piecewise function. So a piecewise function is a function defined by two or more equations. Each piece of the function applies to a different section of its domain. So let's break that down a little bit. If we just have right here x minus 2, if we just have y equals x minus 2, then that would be this line down here, and it would keep going, and it would look something like this. Now in a piecewise, they give us a condition. So they say we have this line x minus 2, but we only want to use this line if x is less than 0. So 0 obviously is right here, and we only want to use this line of x minus 2 when x is less than 0, so when it's on that side of 0. So that is why we take off, really we're taking off this top half, or this top part of the function. We're taking, that's not good, we're taking this off, and we're saying, all right, we only want this bottom part, this part from 0 and into the negative. Now we look at a different function, 2x plus 1, and if we were to graph that whole thing, here's the intercept at the y-intercept at positive 1. If we were to graph it, it's a little bit sideways. If we were to graph it, it would look something like that. But they say we only want to use this line when x is greater than 0. So we take off anytime that x is not greater than 0, and that's how we get this top half right up here. Now, one thing to notice is that here x is less than or equal to, so that means, as you guys know, that we fill in this bubble, and x is just greater than, so that's why we have an open circle here. So we do have to be a little bit careful, pay attention to an open and closed circle, and we'll talk about what happens if we have two closed circles right on top of each other. But that is a quick introduction to a piecewise, where we are given some line and then we're given a condition. Hey, we only want to use when x is less than 0. So we can only, or we only will graph that part of it. So I posed this question. I kind of hinted at it just a second ago. How can a piecewise function still represent a function? Remember, our definition of a function means that for every input, we have just one output. That when we plug something into a function, we only have one output. So a piecewise is kind of broken up, right? There's a big gap right here. But if we're answering this question, if we were in class, this would be a perfect time where I would ask a question, and then the class might be silent, and then I wait awkwardly, and I wait awkwardly, and then I just call on somebody, and then knowing you guys, whoever I call on will give me the right answer, so it'd stop being awkward. But that's how I see this question going in class. Anyway, how can a piecewise function still represent a function? Well, that's because, by definition, we still have one input, or we still have one output for each input. And what I mean by that is if we have our piecewise, let's look back up here. If we have our piecewise right over here, you could give me any value. If we take, let's say we take the value of 2. Well, we look at our conditions. The value of 2 is not less than 0, it's greater than 0. So if we say, well, what is x at x equals 2? It's greater than 0, so we would plug it in right here. At x equals 2, we would get 5, and it would have one input. If we look at our graph, since this is open, at 0, 1, we do not use this line. And since this is filled, we have an input at 0, 0. At 1, 0, we use up here. At 2, 0. And in the negative, we use this bottom line. So how can a piecewise function still represent a function? Because there is still one output for every input, or for one input. Okay, we still have, we call that a one-to-one relationship. And in this graph here, I was going to go past it, but in this graph here, it's no different. Even though we have these open circles where there is no value, it picks it right up down here. If we were to do our pencil test, and we were to say, all right, 1, good, 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 because it picks it up here, and we could see that it is still a function if we run our pencil across that page. So a question that you would see on the homework: write a piecewise function for the graph. And they give you some graph. So how we start out with this is we say, all right, y equals, and we get to do these really cool, these really cool curly brackets, which when I was a student I couldn't do, but all of a sudden when I became a teacher, I could kind of do them. So if you guys can do one of those cool brackets, kudos to you. That's pretty sweet. What we need to do is write the equation for each of our lines. So for this line, we're going to need to write an equation, and for this line, we're going to need to write an equation, and then we'll put some conditions on it. So remember, all these equations are still in this y equals mx plus b form. So we need to find a slope, just like we worked on earlier, and we need to find a y-intercept. So if we look at this first one, if you look here at this line, the y-intercept right away is really easy to see. So we see the y-intercept is at +2, so I'm just going to put +2 right away because that's pretty easy. Our slope, if there's a couple ways you could find this. You could, to find the slope, you could use our slope formula, which remember, y2 minus y1 over x2 minus x1. So that means that you could choose 2 points on this graph, and then you could plug them into our formula. When they give you a nice graph like this, you also can just do a little bit of counting. And you can count, because remember, slope is rise over run. So if we can just count the rise and the run between 2 points, then we're good. So if we choose another point that is right in the cross, so we can know for sure, like this point right here, that would be at 1, 3. And we can just count from here to here. We can count what's the rise over the run. And we rise up 1, and we run 1. So that means our slope is 1 over 1, which would just be slope of regular 1, and positive is good because we are headed in the positive direction. So in other words, if we have these nice even points where they cross the line, we can tell, oh, that's for sure at 1, 3. Then we could definitely use our formula. Don't get me wrong, we could choose 2 points and use our formula, or we could just do a little bit of counting. Maybe you've figured that out by now. Now we need to put the condition on this line. So, and we put the condition on the x values. So when x is greater than 0, we will use this line. And it's not greater than or equal to because we have an open circle. So when these values are greater than 0, so anywhere from here on, we will use this line. That's what we're saying by that condition. Now let's write our other line. We can see right away we have a y-intercept of -1, and then it looks like our rise and our run, again, is just 1. We really don't even have to write in that 1, but it's not bad if we do. Same thing here, we could use our slope formula if you wanted to, but we can also just count how many units we rise, how many we run, and we'll be all set. Now, one thing about this line, it is going in the negative direction, so we can't forget that we have a negative slope. So we need to remember that negative in front of the x. Now let's put our condition. This line starts at 0, so x, but it goes in the negative, so it takes care of all these negative values. So when x is less than or equal to 0, we want to use this line. And we can say equal to because we have a filled in dot, so anytime x is less than or equal to, so even at 0, then we know we will use that line right there. So that is the introduction to a piecewise function. What they will do sometimes is they won't give you the graph, they will just give you the piecewise right here, and they'll say, all right, graph it. So one way you could look at it is you could just look at the equation and you could say, okay, I'm just going to graph this line, I'm going to graph the whole thing, and then I see, all right, well, they only want when x is greater than 0, so I'm just going to erase this part. And I'm going to put an open circle here. And then you would do the same thing with this equation. You'd graph the whole equation, because I know you know how to graph the whole equation, and then you could look at the condition and say, all right, well, we only want when x is less than or equal to 0, so I'm going to erase the bottom half. Now let's look at a step function. A step function is a type of a piecewise function defined by constant values over its domain. The graph of a step function consists of a series of line segments. So with a step function, we have the case where you can see it looks like a piecewise because we have the cool bracket here, but we are given just solid numbers like 50, 75, and the rest of them. And then we are given a range where even from 0 to 1, so even if we have 0.5, then the value that we would look for is still 50. Even if we had 1.5, the result would be 75. And you can see that even if, let's see right here, we had 4.5, well, 4.5 would be here. Where does that go on our graph? Right here in the middle. So a step function, you can see how it looks like steps. It just has, like it says, a series of line segments on the graph and is defined by constant values over its domain. So if we look at the domain, we have a constant value of 50, of 75, of 100, 125, and 150. So I'll show you an example which I think will help. The table shows your phone bill for each minute over your plan limit. Graph the table. So you guys might be too young to remember this, but there was a time in the world where there was not unlimited talk and text, which I don't even know what would happen if some people didn't have unlimited texting. They would go way over their phone limit all the time. So let's say we're looking at how much talk time you get, and let's say that your plan says, hey, you're paying X amount and you get 20 minutes of talk time per month. And then part of your plan is saying, well, if you go 1 minute over your talk time, or up to 1 minute over, then it's an extra 15 cents. If you go then 2 minutes, 30, 3 minutes, 45, 4 minutes, 60. So if we are supposed to graph this table, what we would do is we would have minutes on the bottom, so we go up to 4, 1, 2, 3, 4, and then we would have our cents on the side. I'm going to count by tens, so 10, 20, 30, 40, 50, and 60. Now if we look just here at 1 and 15 cents, if you go, and this would be another question I would ask in class, if you go 25 seconds over your 20-minute max, then how much would you pay? Well, with this phone bill, if you go 25 seconds over, you're still, under a minute, which would mean that you pay 15 cents extra. So if we looked, I guess I should do a little more labeling. Minutes 1, 2, 3, and 4, and this is 10 cents, 20, 30, 40, 50, and 60. So I guess we can backtrack a little bit. If you are exactly at your 20-minute max, then you have to pay extra. No, you don't have to pay that 15 cents extra. If you're 25 seconds over, yep, you need to pay that 1 minute. If you're up to a minute, then you pay 1 minute. For that 1 minute over, you pay 15 cents. Now, if you are exactly 1 minute, like I said, then you pay that 15 cents. If you're 1 minute and 1 second, well, then you pay 30 cents. So here at 30, we go here. And if you're exactly 2 minutes, you pay 2. If you're 2 minutes and 1 second over, then you pay 45 cents. So at 2 minutes, you're good, and you'd pay 30 cents, but at 2 minutes and 1 second, and up to 3 minutes, at 3 minutes, would be your last time to pay 45 cents. Now, hopefully you're seeing the pattern by now, but if you're 3 minutes and 1 second over, then you're paying an extra 60 cents. We go like this. So this is the type of problem you might see with the step function. We won't use step functions a whole lot, but hopefully you can see those steps. How you never would pay something like 20 cents for going over, or anything in between. It's either kind of all or nothing, or you're moving up. Now, an absolute value function, and really when we have the homework, you're going to see the most of the piecewise and the absolute value, not a whole lot of the step function. There we go. So an absolute value function. An absolute value function has a V-shaped graph that opens up or down. So right here, remember I mentioned that parent function earlier, which is like a function at its finest and the most refined form or basic form. Here's the parent function for an absolute value. Right here, right at 0, 0. And we remember absolute value, the value, because it looks like a V. So that helps us out a little bit. So our parent function has a slope, you can see, of a rise of 1 and a run of 1. And it goes both ways. Instead of coming down here in a line, since we have that absolute value sign, it makes that V-shaped. Now we're going to look at how, really what we're going to look at is how an absolute value function shifts. How when we put numbers along with it, how does that change where our function goes or what our function looks like? So first, you can see out here when we add 3 to the outside of that absolute value function, that just moves our function up 3 spots. Okay? What we need to keep in mind is that our go-to kind of base function is y equals mx plus b, where we have the slope and the y-intercept. So when we put this plus 3 on the end, that just is changing our y-intercept. So that's why this function just moved up here. Now the y-intercept is at 3, and we have the same slope out in front. Technically there's not, well, technically there is a number here, there's a 1. So we have that slope of 1. And we'll talk about what happens if this goes negative in a second. So now over here, we have -2, and we're inside the absolute value brackets this time. When we're inside the absolute value, I don't know if they're called brackets or not, I kind of just made that up. Maybe symbol, when we're inside the absolute value symbol, we can see that this -2 will directly affect our x. So that is why you see that our x value moves a little bit to the right. Now the tricky thing is, in here, when we have x minus 2, we move 2 spots. We start here with the parent function, and we move 2 spots to the right. So it's kind of opposite. When I see this minus sign, I think that that means we should go in the negative direction, that we should go 2 spots here. But that is not the case. Okay? That is not the case. When we see this negative sign, if we have inside the absolute value sign, if we have x minus 2 like we have here, that means we move our graph 2 spots in the positive direction. So it's a little bit backwards thinking. On the other hand, if it said x plus 2, then we would move 2 spots in the negative direction. And you'll see how that works out in your homework a little bit more. Last thing, if we do have a negative sign in front of our slope here, then that flips our absolute value upside down. So when it's positive, we're going up, and it looks like a V. When we are having this negative sign out front, then our graph is flipped upside down. This picture right here is one that could be really helpful on your homework. It gives an overview of what happens when we put numbers in with this absolute value symbol. So I'll kind of break it down for a second. I would encourage you to screenshot this. I also posted it on our Canvas page for today, so you can check it out there as well. When we have a number out front of our absolute value sign, like right here, as we saw, this can be a fraction, it could be 1, or it could be greater than 1, so any number. If it's a fraction, that means the function stretches. Okay? So remember, this front number represents our slope, just like with y equals mx plus b. So if it's a fraction, then instead of just being the slope of 1 to 1, or of 1, if it's a fraction, it will stretch it out. If it is something like a whole number, say the slope is 2, then it will shrink our graph and make it steeper. So when we're looking at this front number, it either will stretch or it will shrink our graph. And if it's positive, like we said, it's in the positive direction. If it's a negative slope, then we flip that V upside down. Now, if we look at this, they call it H, but really it's whatever the value is inside of the absolute value symbol. It can be greater than 0 or less than 0, so it can be any whole number. If it is greater than 0, and we kind of ignore the negative sign when we do this, the negative sign is kind of there by default, so just this H, just this value. If it is greater than 0, then we shift to the right. We move to the right. So if it's something like x minus 3, remember minus is kind of the default, so we just look at this 3, then we move to the right. If it is x plus 3, then that means we overrode this negative. So really this would be the same like we said, x minus negative 3, right? That's really what we were saying when we say x plus 3 in this situation. Then we go to the negative side. So out here, we'll shrink or stretch our graph. In with the x, that will move it either left or right. And now this outside value, remember this is our y-intercept with our mx plus b, this will move our graph either up or down. And there's no tricks with this one. If this is positive, if it's a positive 3, then we move our graph up 3. If it's a negative 3, then we move our graph down 3. Okay, so let's look at an example. I know that's a lot. Like I said, I would screenshot this, and as you're going through your homework, refer to it, and that will be helpful. Graph the function. This is just like a homework question. Graph the function first. Compare the graph to the graph of y equals the absolute value of x, or compare it to our parent function. Describe the domain and range. So 3 things we need to do. First, we need to graph this function. So first we look out here. Our slope stays 1, 1, 1. So no change there. If it doesn't have anything there, that means it's positive as well. So we know that it will be a V-shaped looking positive. Inside here, if we look at just this 5, remember negative is the default in here. So when we're graphing, we can look at just this 5. And if it's negative, that means we're going to the right. So 1, 2, 3, 4, 5. And this minus 1, it's a true minus. So we go negative, boom, there's our vertex or our starting point. The slope is 1, 1, and it's positive, so we can just write our regular V. Compare the graph to the graph of y equals the absolute value of x. So compare it to our parent function. Well, our parent function would be here. So we went 1, 2, 3, 4, 5. So we went 5 right, and then we went 1 down. And that's all I'm looking for when we're comparing. Lastly, describe the domain and the range. Well, the domain, so the x values, things are getting muddied up. There we go. The x values, well, this is just going to keep going and keep going and keep going and keep going. So that's going to be all real numbers. And maybe you're familiar with this symbol. It's kind of like an R with an extra bar. Some people write it like this. Not like that. Kind of like that, and draw that extra line. But we can use that. If we're saying it's all numbers all real numbers like that would work. Now our range, our y values, we start at -1, and it could be anything above -1. So we just say y is greater than or equal to -1. That describes our domain and the range, just describing where this will go, and it will never go down here in this y and these y values, so it'll always be greater than -1. Write an equation for the given translation of the absolute value of x. So this time they give us the words, they give us the description, and we need to write the equation. So it might be helpful to graph it. So if we have the parent function, it starts here. This equation that they're describing is 4 units down, 1, 2, 3, 4, and 1 unit to the left, so that means it's right here. They don't say anything about slope, so we just assume that it's a regular slope of 1, 1 and in the positive direction. So if we look here at our kind of beginning, we've taken care of slope. Now what's inside with our absolute value will shift left or right. So we went 1 unit to the left. So remember, it's opposite. So 1 unit to the left would be +1. Be natural to think it would be -1 going this way, but we write it as +1. And then 4 units down, that's true. That's like our, how we think of our y-intercept on the end. Technically it is not our y-intercept here at the end, but that tag on is exactly what it means, just like our y-intercept. So I know that this was a longer lesson and that there are a lot of different things that I threw at you. But if you made it this far and if you stuck with it, paid attention, wrote a few things down, I think that you will do very, very well on the homework. I tried to tailor the lesson and take care of all the different types of problems you would see on the homework. So let's see, students will be able to evaluate, solve, and graph functions written in function notation. Took care of that yesterday. We also looked at how to graph those piecewise, absolute value, and step functions. So we took care of that. Students will be able to compare graphs of linear functions. So these absolute value functions are still considered linear functions, and we just talked about how to compare. Where'd it go? Right here. Like we compared, by our description, we compared this new function to its parent function. Right up here. That's what we did in that description. Students will be able to compare graphs of linear functions. So, again, I know it was a longer lesson. I applaud those who stayed with me. Make sure that if any part of it was unclear or you have questions on the homework that you let me know, and we will take care of those. Otherwise,